All right, that was an unintended interruption, but we continue. So let's see. What I was here indicating that we have a structure. We identified that it was indeterminate to the first, and our choice of redundant, that is what we call to be the extra quantity that if removed brings us back to a statically determinate situation, could be chosen differently. For example, here it is the reaction at B, here it is the moment at A, here it is the introduction of a hinge somewhere within the span. Okay? Now, so far I've used examples of indeterminate. Oh, by the way, yes, just to emphasize, what is the value of x1 here? Well, obviously sufficient so that this sketch has no deformation at B when this has the correct value. What is the value of x1 here? Whatever x1 has to be so that at point A there is no rotation due to the load and due to x1 added together. What is it here? Well, the value of x1 is such that the slope on the left and the slope on the right of that hinge are the same, so that continuity has been preserved, right? So we are using compatibility to find the values. Geometrical constraints to find the values. Now, thus far I was talking about indeterminate to the first degree. There was only one thing we didn't know. So let's look at one case that is a little more. So consider this frame, right? So if we look at that, you can either use your method of opening it into a tree or whatever, but we can see that this structure is indeterminate to the third degree, right? We could remove all of this. And let's say it's got some loads. We don't care what they are, right? So what are the options? Well, there are many options. One that is kind of obvious, most people probably would use, is to say, okay, this reaction is my first redundant, this reaction is my second redundant, this moment is my third redundant. Because this structure is exactly equal to this one, right? Given correct values of x1, x2, and x3. How would we compute the correct values of x1, x2, and x3? Well, if x1, x2, and x3 did not exist, right? If they were 0, because we can say this is equal to, the structure with the loads are here, right? But let's say you didn't have x1, x2, and x3. Then this structure will, I don't know, let's say deform to here. Maybe this one deforms to there. So maybe it's like this, right? So this point has moved downward this amount, A. This point has moved to the left this amount, B. And this point now has an angle with respect to the vertical, C, right? In reality, on the real structure, this point has no movement down or up, no movement left and right, and no angle because it's fixed, right? Therefore, when we apply the values of x1, x2, and x3, no loads, right? Because we've already applied the loads. The loads make it move like this. When we now apply the values of x1, x2, and x3, we must have this point move up to the right and to have a slope in the other direction. So, for example, this could be, I don't know, maybe like this. Let's see, I wanted to have this like, no. Right, that's not a very good deflected shape, but because it wouldn't really deform like that, I could do better. But the point is that this thing will move up from where it used to be by an amount that has to be A. It has to move to the right by an amount, actually, you know what, this is bothering me just looking at it being wrong. The frame is here, frame is here, and then we do this, and then this. So if I draw this joint slightly this way and slightly this way, I would draw this joint. So this goes like this. This could move to here, let's say. The angle of 90 degrees has to stay the same, so this joint just rotated. And then due to this, depending on things, this could be like that, right? So now we have that this point has moved a certain amount horizontally, has moved a certain amount vertically, and has a certain angle. The horizontal, I'd said, you know, it's N1, the vertical is N2, and the rotation here is N3. So X1, X2, and X3 must be selected such that, right, N1 is equal to C in absolute value so that they cancel. N2 is equal to B, and N3 is equal to C, right? Therefore, this plus this satisfies the constraints of the original structure, which has no horizontal movement, no vertical movement, and no rotation at that point, right? Okay. Let me clean up and illustrate the last case, qualitative. This requires a little bit of all right. So finally, one more. Let's consider this structure, which we looked at one time before. It's got some load here, right? Then we say, is it determinate or indeterminate? We discussed it in the previous lecture and concluded that even though we could calculate these reactions, this structure is indeterminate to the third degree, because to open it like a tree, you have to cut it open so that you can take a free body diagram and go through without adding 6 unknowns, right? So this is indeterminate to the third degree. Now this is a case where you have no choice. You cannot take the reactions as redundants because the reactions are needed for static equilibrium, right? So in this case, you have a few choices, but they all involve cutting through here. For example, one option is you could say that, now this is drawn with a hole that is huge, but in fact what I mean is just this, right? I just open the hole. Now when I cut through there, the axial force is something that I would remove. The shear force is something that I would remove, and the moment is something that I would remove. So my redundants are x1, x2, and x3 being axial shear and moment at the place that I cut the structure open. Then we would apply the load, right? The structure will deform, and this point, which is like in reality connected, would actually do something crazy like this, right? And so we would need to have values of x1, x2, and x3 to splice it back as it should be, as a continuous bar at that location, right? So that's one option. You could also instead of choosing that x1, x2, and x3, you could perhaps choose to put a hinge here, and a hinge here, where here is anywhere you want on that bar, right? In that instance, here is my loading. We could say that our first redundant would be here, our second redundant would be here, and our third redundant would be here. And the values of x1, x2, and x3 would be such that when the structure has the hinges, right, the loading produces different slopes on either side. Different slope on either side, different slope on either side. x1, x2, and x3 are such that once they are acting, the slopes go back to being continuous at this point, right? Or everywhere, because the structure does not have any hinges at that location. So, let's now start formalizing things. This is my best shot to give you some idea about what's the qualitative problem that you're looking at. I mean, the problem from a qualitative perspective, right? So now, let's illustrate with this beam. I mean, let's formalize with this beam. So when we face an indeterminate structure, our first and fundamental step is we must be able to determine how indeterminate it is. If we do not get how indeterminate it is, then there's nothing to do, because everything will be wrong after that. Therefore, it's necessary to be able to say, okay, this structure is indeterminate to the second degree. The second step is to choose what are the redundants that you want to use to solve the problem. There's two of them because we said it's indeterminate to the second. But as I've been trying to illustrate in the last 20 minutes or whatever, there are many choices. All of the choices are, from a theoretical perspective, equal. From a practical perspective, sometimes one choice is easier than another. So let's say in this case, we say that our second step is to identify what are our redundants. Give them names and show directions. So we are saying here that these are our redundants. My thing here is, okay, here it is. Okay, so these are my redundants. So these are our redundants. So not only did I say here that they are at these 2 points, these 2 reactions, but I've also shown what I consider my redundants to be positive. Now, because this is a lecture which I'm introducing the topic, I am kind of overdoing it with drawings, but let's say now that the structure without redundants, but with the loads, it's another sketch you want, and that's called the primary structure with the loads. So you want to draw the primary structure and show the loads acting on it, the original loads. What is a requirement of the primary structure? If you've done it correctly, the primary structure is statically determinate. That is, you can solve it using only statics. Okay? So that's your primary structure with the loads. And we could say that on the left side of the page, until you become proficient of this thing, you can say that you always will do this. This is the problem. That's how indeterminate it is. These are my redundants. I show which directions they are. This is kind of extra or redundant in itself, but here is my primary structure with the loads. Okay? That's fine. It's all qualitative. Now, I start again but because I don't have enough space here, I'm going to erase, right? So now we have okay, now in the solution part, we have, oops, it's still wet. So now we get to the solution and we say the primary structure with the loads, this is called the P-sketch. So we draw the primary structure with the loads again. That's the P-sketch. Then we have the x1 equal to 1 sketch. In our case, that would be this. And then we have the x2 equal to 1 sketch. And of course, if there were 3, they would have the x3 equal to 1 sketch, the x4 equal to 1 sketch, the x5 equal to 1 sketch, and so on. Therefore, there is always, let's see, x1, okay. So this is the P-sketch, which is the primary structure with the loads. And then there is a sketch of the structure with no loads, and each one of the redundants taking unit values. Okay? Now, when the primary structure takes the loads, the primary structure will undergo deformations, right? And we now are going to assign names to those. So the deformation of the primary structure at the location of the first redundant, or if you'd like, the formation of the primary structure in which the first redundant does work is a more precise term. It's called delta 1. The deformation of the primary structure at the location where the second redundant will do work is delta 2, right? If there was 3, 4, 5, then there would be delta 1, delta 2, delta 3, delta 4, delta 5. If it's a rotation, we still would call it delta something, right? So our notation delta is generic for the deformations at the locations of the redundants or the deformations that are work compatible with the redundants, okay? I'm not pretending to show them here. I'm showing them just for intuition in the directions that they would occur, not in the directions of the positive, but that should be obvious as we write the equations. Now, the structure with the 1 kip load will also suffer some deformation, right? And we also are interested in giving names to those deformations. So these deformations are called flexibility coefficients, and this would be F11 and this would be F21, where Fij is the deformation at I due to a unit load, although it could be moment, at J. This was the P-sketch. Okay? So this is F11 because this is the deformation at 1 due to a unit load at 1. This is the deformation at 2 due to a unit load at 1. This one gives us a deformed shape like this, and this right here would be the deformation at 1 due to a load at 2, and this is the deformation at 2 due to a unit load at 2, right? So I'm going to put these things on the left side so I clear the right side of the board. This is P, this is x1 equal to 1, and this is x2 equal to 1, right? Now, at this point from this sketch, then we want to enforce compatibility, right? So we can say, let's look at point 1. Oops, I'm sorry, I didn't draw the real structure at all somewhere, right? The real structure has a support there, and a support here, and the loading, right? That's the real structure. So this is our primary structure with the loads, our x1 equal to 1 sketch, our x2 equal to 1 sketch. Now we say, okay, let's look at the deformation at point 1. The algebra will take care of things. On this sketch, the deformation is delta 1. On this sketch, the deformation is what? Well, is f11 times x1, right? Because this deformation is f11 if this is 1. But if x1 was 2, it'd be twice as big. If x1 was 7, it would be 7 times as big. Because what? Because we're dealing with a linear system, a linear structure, therefore I can do this. The deformation here due to the x2 on the same token is just f12 times x2, right? And then we can say, but what is the deformation at that point? Well, that in this case, that deformation is that one, and that deformation is 0, right? Now we look at the other point and we say, okay, delta 2 is how much it deforms on the primary structure without those redundants. We have f21 times x1, and we have f22 times x2, and that must be 0 also, right? So we have two equations with two unknowns, and we should be able to solve them. Now, normally we write this like this. I mean, not normally, but gathering in a matrix framework. This would be f11, f12, f21, f22. This is x1, x2, and that's equal to 0, 0, right? Now, to write it in even shorter notation, we write delta plus f times x, in this case, is equal to 0. So our problem is to solve this system of equations, right? And we know how to solve them, so when we solve them, we have x. Once we have x, then the structure that we're dealing with is no longer statically indeterminate, because we already know what are these two reactions, and therefore instead of thinking about them as being reactions, we just simply think about them as being loads. And so what we have is just a cantilever beam with a load here, which is x1, and with a load here, which is x2, and we just get whatever we want. Shear, moments, etc., right? Now, let's see what is involved in solving this problem, this one in particular. So we have to calculate delta 1, that's one thing, right? We have to calculate delta 2, that's another thing. We have to calculate f11, f12, f22. I will now show you that f21 is equal to f12. So it looks like 1, 2, 3, 4, 5 with the argument that these two things are equal, as we shall see now. Now, why are they equal and how we calculate all of them will be apparent from the time, from where we go. So now let's use our know-how on the computation of deformations. So now forget about the fact that we're dealing with indeterminates or whatever. What we're doing now is computing deformations. So if you want to calculate delta 1 in this structure, you have a cantilever, it's subjected to some load, you want the deformation at that point. What is it that you do? Well, we just took the exam. We've been dealing with this and hammering it for the last 3 weeks. So I would expect that all of you should say, since I want to calculate the deformation there, I put a unit load there. Well, I already have it right here in this sketch, right? And then I calculate the MPs over here, and I calculate the M1s. I multiply and I integrate, right? Therefore, what do I find for delta 1? What I find for delta 1 is that I multiply the P sketch times the x1 equal to 1 sketch, integrate, that gives me delta 1. We got that one. Now let's get delta 2. If I want to calculate delta 2 on that structure, what is the first thing that I do? I put a 1 kip load at delta 2. Oh, I already got that. That's in this sketch, right? And then I calculate my MPs. Well, we already have them. And I calculate my M1s here. And then I integrate my MP over AI curvatures times my M1s. And I get my delta 2. So delta 1 is this sketch x1 equal to 1 times sketch P, and F22 is sketch x2 equal to 1 times sketch P. So we got these two down, right? Now let's calculate F11. What is F11? F11 is this, which is the deformation here due to a unit load, right? But what do I do if I want to calculate the deformation there? Well, I put a unit load. So that means that this sketch is both the load and the unit load to calculate F11. Therefore, the MP and the M1s for the F11 are just this sketch. Therefore, to calculate F11, we multiply the x1 equal to 1 sketch times the x1 equal to 1 sketch and integrate. Now, I want to calculate F21. Got that one down, right? So let's put a little cross. So now I'm at that one. So I want to calculate F, or maybe F12, let's say. F12. So I want to calculate the deformation here due to a unit load here. Therefore, that's F12. Actually, let me just say F21. Let's see. Yeah, let me say F21 so I stay in this sketch. So if I want to calculate F21, that means I want that deformation, right? So what do? I put a unit load here because that's what I want to calculate, the deflection there. But a unit load there is here, right? And it's due to this. Therefore, F21 is sketch 1, which plays the role of MP, times sketch 2, which plays the role of M1, and I'm multiplying. Bottom line is that F12 is sketch 1 times sketch 2. Obviously, F12 and F21 are the same because it's just this times this or this times this, which is the same thing, right? Now we've got that one and we've got that one. And now we're left with only what is F22, which is the deformation at 2 due to a unit load at 2. Therefore, this is the cost and this is the 1 kip load there. And therefore, F22 is just sketch 2 times sketch 2. Okay? Therefore, as I mentioned before, since you have the tools of we needed to develop the ability to calculate these deformations because the ability to calculate these deformations is what allows us to take your expertise from statically determinate structures to statically indeterminate structures, which becomes just a sequence of deformation calculations, right? And then solving a set of linear equations. And stepping even further back, in order to calculate these deformations, you have to rely on your expertise to do statics and to write equations for moments, shears, and axial forces in case that they are needed, right? Now, there's only one more thing to say here before I solve an example for you, and that is that the right-hand side need not always be 0. For example, we could say that this problem had these loads, right? at those loads. But in addition to that, point 1 and point 2 were known to have movements, settlements, thrusts, whatever. So the final values need to be known at the position of the coordinates, right? 0 is just one special case of what it is to mean to know it. If instead of 0 this was known to be 1 inch and this was known to be ½ inch, that's just as good as 0, right? So what we say then is that the flexibility method or the force method writes like this. Delta, I won't even put the bracket thing, which is the deformations due to the loads, right? This is the deformations due to the loads on the primary structure when all the redundants are 0, right? Then you have the flexibility matrix, F, which is just the listing of the flexibility coefficients in a matrix, times the redundance, X, which is just a list of the X's. And then the right side need not be 0. It is most of the time, but we just call it delta. So the flexibility method in general is just this. This is the flexibility matrix. These are the redundants. And these are the final movements, if any, at the location of the redundants. And the problem, no matter how the structure looks, is always that. So it is, in fact, all the problems, if I change this for delta 1 and delta 2 to be generic, all the problems that are indeterminate to the second degree look like this. All of them. So it's not like I got a different problem indeterminate to the second degree and I got to figure something out. No, it's indeterminate to the second degree, it's that. Okay? It's indeterminate to the third degree, there's one more here, this expands to 3 by 3, and these are 3 entries. And so on. So, let's see. Let us erase clean and solve an example for you. Okay, so let's do a specific example. Let's use that same beam, and let's use a loading that will make life quite easy. So let's say our structure is loaded with a moment Q acting at that point. Okay? So this is the problem that we're going to solve. We're going to say that this distance is L, this distance is L. Our objective is to draw the shear and the moment diagrams. Okay. In the homework that I am going to give for you, it's going to be this first homework. It's going to be the same problem, exactly the same problem. The only difference is that instead of choosing the redundants that I will now choose, you will choose a different set. Okay? You will choose a different redundant set, but the problem is the same. I will mention it at the end when we finish solving this one. Okay, so here we are. What we've already discussed it, so we know that this is indeterminate to the second degree, right? I'm going to skip the first three sketches that I said. This is the structure, these are my redundants, this is my loads with redundants. Just go to the solution sketches. So we need a sketch which is the P sketch, right? That is the sketch of our loads with no redundants. Well, actually, let me draw them here quickly, just to be not to be so sloppy. So these are my redundants in the way I'm going to solve the problem. X1 and X2, right? Those are the redundants. So this is my P sketch. Then my sketch X1 equal to 1 is this. And my sketch X2 equal to 1 is this. So I have my P sketch, my sketch X1 equal to 1, my sketch X2 equal to 1, and then I know that my problem looks like this. Delta 1, delta 2, plus F11, F12, F21, F22 times X1 and X2 equals to delta 1 and delta 2, but I have no prescribed motions at these 2 points, and therefore this is the typical case where the right side is 0. So we have 1, 2, 3, 4, and 5 deformations to compute. But they will all be real easy, right? Once we have the, we're going to do the calculations. Of course, each one of these things could be computed as precisely as possible, which would be, in a case of a beam, including bending and shear, because there is no axial, right? But as we've already discussed repeatedly, the bending will dominate, and we normally do not account for the shear because it doesn't really add anything to talk about. So I go to my P sketch and I say, all right, I'm going to select a coordinate that begins from this side, called X. Well, actually, I didn't really need it here, but just thinking about what's going to happen afterwards. Since you guys have done this quite a bit, I'm going to try to have to erase less. I take the bubble, right, around here. So I won't draw the bubble so I don't have to erase it and make a mess. But if I made a bubble like this, it would look like this, right? There would be Q here. This would be the distance X. And this would be the moment that we're trying to find, MP, right? There would also be potentially a shear and an axial. And from there, you can see that my equation is MP in my P sketch is just Q. And I've already selected that to be the positive sign, right? Now I get here. My bubble before I get to this one is 0, right? And my bubble after this one looks like this. Here is the 1, whoops. Here is the 1 kip. This is X. The distance from here to here is L. Therefore, the distance from here to here is X minus L. And I have my moment here. Let's see, this is like this. So I'll choose it like that in order to have a plus. And so here is my shear, here's my axial. Now you might see that my MP here is clockwise, and I decided to choose my M1 as the other way in this sketch. It doesn't really matter, right? Because this is a segment that has nothing to do with that one. I have to just to be consistent every time. So in this case, summing moments about here, I would get minus M1 plus X minus L times 1 equal to 0. And so we find that M1 here is equal to X minus L, and our sign convention is like that. Okay, now in this one we look at the bubble and we find that M1 in this case let's see, I have to take it like this. So here is my, did I do this right? No, I did not do it right. So I don't know why I put the one keep loading the wrong direction. So my apology. Let me erase that and get it correctly, okay? So dismiss this last second. This is final to there. I don't know what happened to me. So I'm looking at this. The answer is going to be okay, but if I take the cut, what I meant is I have a 1 here like that, right? My distance x is this. My distance L is this. From here to here is x minus L. And that's against the clock. So if I want my moment here to end up being plus, I would have had to choose it like that, right? So in that sketch, my M1 is minus x minus L plus M1 is equal to 0, and therefore M1 is x minus L. Okay? Now finally, in this sketch here, I take the bubble, and we have the 1 up, the distance is x, the moment is M1, like that. And here I don't have to make distinguishes between the two parts, because for the whole thing, we can get that M1 is just simply x, right? Okay, so I erase this. But I need to be able to see my P sketch, my x1 equal to 1 sketch, and my x2 equal to 1 sketch, right? Those have to be present every time. So, as far as when we are working, this is the most important part. These sketches must be drawn sufficiently large, they must be drawn very clear, and you should keep, even though I could not keep them here because I need the space to work, you should keep little sketches that allow you to remember or to see what did you assume to be plus, right? What did you assume to be plus, so that you can be, so that you know that all, well actually no, I take that back. Once you have this thing, you've already established what you assume to be plus, so you've made that decision. I guess when you're making this sketch, you have assumed the direction, you have to make sure that your directions are consistent in your 3 sketches, right? Now that they are like that, it's just a simple matter of saying, let's see if I can do it so that everything fits. What is delta 1? Delta 1 is the P sketch times the 1 sketch. So that is, I'm going to put the EI on this side so I don't have to divide by EI every time. So that's going to be the integral of this times this, right? This integral is 0 in the first part, so L begins at, x begins at L, ends up at 2L, and we have Q multiplied times x minus L ds, but S is running with the bar, so it's dx. Therefore, this is equal to Q times the integral of x. Dx is x squared over 2 minus L, and the integral of dx is x. And this is between L and 2L, and that's the same thing as Q. It's not going to fit. So that's the same as Q multiplied times 4 over 2, 2L squared minus 2L squared, right? Minus L squared over 2 minus L squared. Let me see if I didn't make a mistake. Q minus L So x dx is x squared over 2, L is x, Lx. Those are the limits. I get 4 over 2 is 2, 2L squared minus 2L squared minus L squared over 2 minus L squared. So it looks like these two parts cancel over here, and then we get L squared minus L squared over 2, which is L squared over 2, and that's it, right? Let me see, because I think I calculated it. Yes, that's correct. So we have then that EI, no, why do I want to put EI? We have then that delta 1 is equal to Q L squared over 2 EI. Put it in a little box, and we go on to the next one. Now we calculate delta 2. So EI times delta 2 is the integral of the P sketch times the x2 equal to 1 sketch. Integral, in this case, they both go from all the way from 0 to L, or 2L. So I can go from 0 to 2L of Q times x ds, but that's just dx. So that's just Q times x squared over 2 between 0 and 2L. So that's just Q times 4L squared divided by 2, which is 2L squared, right? And therefore we have that delta 2 is equal to Q L squared, 2QL squared divided by EI. Right? Let me check that one. Yes, 2QL squared divided by EI. So we got that one done. Now we want to calculate F11. So EI F11. Of course, I can put the EI on this side because the EI is the same everywhere. Otherwise, I'd have to put it where it belongs, right? So it's this sketch times this sketch, 0 times 0, and then this part, right? So it's the integral from L to 2L of x minus L squared, which is the same thing as to say x squared minus 2xL plus L squared dx, right? You can do that integral, and it turns out that it proves to be, I'll just skip the algebra because it's very simple, right? So we find that it is equal to L cubed over 3. Excuse me. So it's L cubed over 3. So we find that F11 is equal to L cubed divided by 3 EI. Okay? Then we need EI times F22. And F22 is this sketch times itself. So that is simply the integral from 0 to 2L of x times x again dx. And that's x cubed over 3, right? From 0 to 2L. And so that's 2, 4, 8/3 of L cubed, right? And so we have that F22 is equal to 8 L cubed divided by 3 EI. Okay? And we have only F12 left. And unfortunately, I don't have space, so I'm going to have to erase something. And I guess what I'll erase is this computation and just leave what the answer was. Right? And so we'll have that EI times F12, which is the same thing as EI times F21, is the integral this times this, right? Sketch 1 times sketch 2. 0 over the first part, and then it's just the integral from L to 2L of x multiplied times x minus L dx, right? And that integral, you can crank through it, and you get 5/6 of L cubed. And therefore, F12 equals F21 equals 5/6 over EI L cubed. And now we have everything. Okay? So, at this point, we're done. At least with the calculation of the deformations. And we can, I want to keep these sketches here all the time, so I'm going to erase these things. I know what the values are, and so I'm just going to put them on the matrix form. It's getting very dirty. Okay, so this was the real problem. This is the problem with the Q here. This is the x1 and x2, right? So I'll put like this, a line, try to stay on this side. Then we have that our equations are like this. EI, no, not EI. EI was in the denominator. It's L cubed over EI. The matrix is 1/3, that was F11, 5/6, F12, 5/6, and 8/3. That's just plugging them in. This is x1 and x2 plus delta 1 and delta 2 were 0.5 QL squared and 2QL squared divided by EI, and that was equal to 0. So those are the two equations with two unknowns. So we do this, the EI's cancel. We can divide by L squared, or by L cubed, let's say. So dividing by L cubed and multiplying by 6. Dividing by L cubed and multiplying by 6, this becomes a 2, this becomes a 5, that becomes a 5, and that becomes a 16, right? And then this is x1 and x2. Take this thing to the other side, and so it's a minus. I multiplied by 6, so anyway QL squared is outside. And since I multiplied by 6, this is a 3, and this is a 12, right? So it looks like that, right? 2, 5, 5, 16, x1, x2 minus QL squared, 3 and 12. Well, it doesn't matter. I mean, I can go through the steps, but what is the point, right? You solve it, and you get x1 equals to 12/7 of Q over L, and you get x2 equals minus 9/7 of Q over L. The first thing you notice, or you should note, or you should make yourself think this way, is that x1 and x2 are forces, right? They are these two reactions. They have to have units of force. Q is a moment. Therefore, moment, which is feet, divided by feet, is force. So at least the form is unit-wise consistent. If you find yourself saying that x1 was something Q only, then that has to be wrong, because it's not even has the right units. Or if it was Q over L squared, that would be wrong too, right? It has to be Q over L in order for x1 and x2 to have the right units. Now that we know what x1 and x2 are, we can actually start from scratch, which is fine. Or if you'd like, you can realize that any question that you want is simply regarding shear and moment, or no, at least regarding moment, because we didn't draw the shear. For example, what is the moment everywhere? Well, it's the moment here, which is Q everywhere, plus this equations multiplied times x1, plus this equation multiplied times x2, right? So you can do it like that. I'm not. In this particular case, I'm just going to write here that x1 is equal to 12/7 of Q over L, and that x2 proved to be minus 9/7 of Q over L. What does the minus mean? The x1 is up, which is in the direction assumed, and the x2 is down, because it's in the direction you got a negative, right? So now that we have them, we can erase this stuff here to make space to draw our shear and moment diagrams. So we go back to our original problem and we say, okay, what is x1? Is here, is 12/7 of Q over L, and x2 is here, is 9/7 of Q over L, and there was a moment here, Q. That's our original problem already solved, in which the redundants have become known values, right? Okay, now we want to draw our shear and moment diagrams. There is no need, I could have done it from the left to the right, but I'm just going to be very clear by saying, okay, I'm going to calculate the reactions. So some of the forces in the y direction show you that over here there has to be a vertical reaction, which is 3/7 of Q over L, right? 3/7 down plus 9/7 down is 12/7 up, right? If you sum moments about here of everything, you find that there is a moment here of Q over 7. So from a free body diagram of the complete thing, you find that this reaction for this moment is Q over 7. From some of the forces in Y, this is 3/7 of Q over L. Now, we can draw, let's see, our shear. So our shear begins from 1, 2, and 3/7 of Q over L, and is negative in the way that we normally draw shear diagrams, right? Because we normally draw shear diagrams such that the left side reaction on a beam is up, the shear will be plus. So that shear is negative. It takes a jump of 12, so it goes from -3 to +9. 1, 2, 3, 4, 5, 6, 7, 8, 9. So somewhere around here, right? So this is -3, well, actually it doesn't need a minus, 3/7 of Q over L. Well, actually, yeah, let me put the minus. And there, plus 9/7 of Q over L. And then it goes flat, and it goes to here, and it finds that reaction, and it closes down, and that's our shear diagram, right? And then our moment diagram, which we normally would plot on the compression side. So this moment here is putting compression on the top of the beam, right? This Q is putting compression on the top of the beam. So we would plot that on the top side as Q over 7. Now, the area under the shear diagram, there's many ways to do this. I'm just going to do it with the, I could do all kinds of things, but let me use the shear diagram. So the area under the shear diagram from here to here is -3/7 of Q, right? Because it's multiplied times L. That means that this is the change in the moment from here to here. So since we were at Q over 7 plus, and we subtracted 3/7, we must have 2/7, right? So at this point here, we have 1 and 2. And so here we are at minus 2q over 7. The slope of the moment diagram is equal to the shear, so that slope is negative 3/7 of q over L. The area under here is 9/7 of q, right? Because it's positive, it's the area under the shear. So the change from here to the end is adding 9/7 to this minus 2q7, which would give you what? 7/7, which is 1. So this would be 1, 2, 3, 4, 5, 6, 7. So this would go like this, like that. And so our moment diagram is this. And our shear diagram is this. Right? And we finish the problem. You can confirm that this moment diagram here is just the sum of that plus this, that plus this sketch multiplied times x1 plus this sketch multiplied times x2. You add them together, you get that plot. Okay? So, that's it. Now for homework, for your first homework on this, I'm going to make it, how should I say, I'm going to make it very simple so that you can do it quickly and be ready for the next class on Monday where we try something a little bit more complicated. So this is the structure we just solved. And I want you to solve it using this redundance. Okay. So select this redundance and solve it. Of course, you already know the answer, right? Because what are these redundancies? They are the values of the reaction here and of the moment at this end. We just solved for them, right? So if you do the problem right, x1 has to be, this was down, I believe, right? So x1 is going to have to get what? Minus 3/7 of q over L if you get it right, and x2 has to be q over 7, right? So you know what your answer should be if you do it correctly. So get it done by Monday, and I'll see you then.